Hello my dear friends, in this video we will going to learn about the heat transfer mechanism through entropy. See, we already know that entropy transfer mechanism, that means a difference between SI and SE, that means entropy entry minus entropy exit, is by two mechanisms. First is the heat transfer and other is the mass transfer. So we'll discuss by heat transfer. So for that, what is that? See, since we know that heat is a form of energy. What is that? Heat is a form of energy, and that this form of energy is very disorganized manner, form of energy which is disorganized manner, very disorganized manner. So we already know that entropy, the cause of entropy change, cause of entropy change is due to disturbance, disorganization, randomness, like that. So if we supply heat to the system, along heat the entropy will enter to the system, and for that entropy of the system will increase. When you take a heat from the system to the surrounding, so if you take a heat, that means you are taking a disorganized manner situation of the system. So the disorganization of the system will increase or reduce? Will reduce. So entropy will reduce. So heat along with the heat, so why? Because heat is a form of energy which is very disorganized manner. So if you think about, there is a container in which there is entropy. There is a container in which there is entropy. If you mass, if you energy, then you have energy, entropy. And if you supply a extra disorganized manner, so if you supply a heat, that is you supply heat, so the disorganization of the system will increase or decrease? Will increase. So entropy of the system will increase. Again, if you think about in a reverse direction, if you extract a heat from the system, so what is you are doing? What is your job? Your job is that you are extract from a system to the surrounding a disorganized manner. So the disorganized condition of the system will increase or decrease? Will decrease. So along with the heat, the entropy will transfer. So disorganization manner. So some disorganization. So what is that? So some disorganization, that means entropy. Entropy will flow with heat. Suppose if there is you have a system like that, if you have a system and this is your system, right? This is your system, any system, right? And this is your system, right? And is the system boundary temperature, let's suppose the system boundary temperature TB is equal to 400 Kelvin, let's suppose, right? And you supply heat to the system, let's suppose you supply heat to the system, Q is equal to 500 kilojoule, let's suppose. So we know that heat is in a disorganized manner. So if you add the disorganized condition disorganized situation to the system disorganization will increase or decrease? Will increase. So system entropy will increase or decrease? Will increase, right? So entropy transfer या entropy flow both term flow by heat, that means entropy by heat, this is your in is what? Q from system by temperature of the boundary, right? And what is that? This is your 1.25 kilojoule per Kelvin. Mind it, this is your boundary temperature. This is your boundary temperature. Boundary temperature, and which is fixed, constant, right? Okay, so this is your entropy transfer. So the entropy transfer with respect to heat is nothing, it is the ratio of heat to the temperature across a boundary at which the heat will transfer. So what is Q? If T is not constant, let's suppose T is not constant. T is not constant. See, if there is a system, here another temperature, this is the system boundary have another temperature, this is the 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 boundary have another. So different temperatures. So let's suppose this is your T1, T2, T3 like Tk, in which the heat will transfer in, suppose Q1, this will Q2, let's suppose here heat will reject Q3, let's suppose here Q4. So in this condition, what is the entropy transfer? So in this condition, what is the entropy transfer? S heat through net heat transfer is what? Summation of Qk by Tk, right? Summation of Qk by Tk during a process, summation of Qk by Tk, where Qk is the heat transfer through a boundary at temperature Tk at a location K, right? So this is your net entropy transfer, okay, through heat, right? Second point is that work is done on the system but work is very important, work is entropy free and no entropy transfer by work. So entropy transfer by work is is equal to 0. See here, since entropy, see if there is a flywheel, see this is your example source pKnag, and this flywheel take as a system, right? And if you supply a work from external, this flywheel will rotate, right? During that rotation, this flywheel constitute different molecules. If you supply a work to rotate the flywheel, is there molecule will disturb? No, that molecule, it as fixed location it will rotate, so the molecule doesn't disturb. So during work supply to the system, the randomness will be not disturbed. Okay, like that, if you take a piston cylinder arrangement, right, and if you churning the device, right, this is your system, like that, this is your system. If you churning the device, that means you do a work, shaft work, right? If you rotate, so there is entropy transfer? No. Why? Because this is a closed system, no mass transfer, and also there is a insulated, so there is no any heat transfer. So when the work will done, that work will dissipate into its internal energy. But if you supply a heat, that heat will not dissipate, it will directly heat up the system boundary. So if you work will do, that work dissipated into internal energy, that internal energy will generate its internal entropy. So here is the generation is there, right? But entropy transfer, that means net entropy transfer is 0. So if generation is there, so delta S of the system is what? S generation, and this is always increase, so this system entropy will increase, but there is no any entropy transfer, so through a work transfer there is no any entropy transfer. Number third point. Number fourth point is that since energy transfer by heat, work and mass, right? Let them by heat and work, energy transfer by heat and work, right? But entropy transfer, by heat only. See, this is the beauty of a second law of thermodynamics. This will clear understanding what is the, here at this point we clearly understood that what is the difference between heat and work. It is the second law to exact differentiate what is the difference between heat and work. So heat and work is responsible for energy transfer, but not work it is only heat to transfer entropy. Why? Because heat is a disorganized manner. So we can say that only heat transfer is the energy interaction, but right, so work is not responsible to transfer any entropy, right? Number fifth point is that, what is that? Number fifth point is that, see, if there is a system and this is your piston cylinder arrangement, right? This is your closed system, mind it, and there is insulated here, there is insulation, right? You do a work on it, this is your system, you do a work on it, which is shaft work. How? By churning, that means this is your system, this is your system, this is your system, this is your system, excluding shaft. So work will done. Now there is a thing is that entropy is not transferred here. From here entropy is not transferred with work, but from this paddle wheel, why? Because this is rotating, entropy generation via friction, so entropy will generate via friction. So what is the system entropy? Delta S of the system is what? S in minus S out plus S generation, right? This is 0 because no heat transfer, no mass transfer, and S generation is greater than 0. Why? Because it is, generation is the internal property, internal to the system. This is the internal, it is internally irreversible. Why? Due to friction. So what is that? System entropy will increase or decrease? It will increase, right? So though there is no entropy transfer across the, so this is a very important. So this is your, what is that? Though there is no any entropy transfer, so what is that? We can write here like, though there is no entropy transfer across the system boundary, but system entropy will increase because of where we can write because of entropy generation with the system as work. System as work is dissipated into a less useful form of energy. See, though there is no entropy transfer across the system boundary, but the system entropy will increase. Why? Because entropy generation with the system, why? As a work is dissipated into a less useful form of energy. So there is a one mark in the point is that when you transfer a work from the start of the system, if there is a less viscous fluid, so this work will be responsible to displace more and more system boundary. So this is your useful work. So less and less useful unuseful work. So less and less unuseful work, less and less entropy generation. So entropy generation is what? What is the meaning of the entropy generation? Entropy generation is solely responsible to useless form of energy, right? Useless form of energy. So higher is the higher useless form of energy, higher is the higher energy entropy generation. If the lower is the lower useless energy, the entropy generation will lower and lower. And see, if the process is reversible, if you assume that the process is reversible, if the process is reversible, so maximum work will develop by the system when the expansion of the boundary. So maximum work will develop by the system. So less and less work will waste, less and less work will waste. So less and less usefulness of usefulness energy will waste. So less and less entropy generation. So less and less entropy generation, more is the more reversible, right? But there is always dissipation. Why? Because there is but in this case there is always dissipation. Why? Because there is a viscous. If there is a viscous, then there is a chance to dissipate that energy more and more, which is in the form of work. So that work will dissipation more and more in the form of dissipation via friction. So more and more entropy generation. So if more and more entropy generation, more and more its reversibility. So entropy generation is something say about the extent of irreversibility. So higher is the higher entropy generation, higher is the higher it is irreversible. So this is your, so there is a one term, keep in mind that lower is the lower yeah, less lower is the lower useful unuseful work. full of energy. Lower is the lower unuseful energy. Lower is the lower unuseful energy. That means higher is the higher useful energy. If higher is the higher useful energy, lower is the lower dissipation effect. If lower is the lower dissipation, lower is the lower entropy generation. If lower is the lower entropy generation, if lower is the lower entropy generation, higher and higher and higher it is reversible. Higher and higher is the reversible, right? So higher is the higher it is the reversible. Higher is the higher work output, right, during expansion of work. So if you think about that, if there is a cylinder and this is your piston, if you think about that, and this is your system, if the system boundary being this the process is frictionless, that means reversible internally or externally. So the work developed, boundary work is the maximum, right? Work developed, that means a boundary work is the maximum. And if there is a another situation, there is a gas and there is a system and this is your vacuum. If you puncture it, so what is the work? Is zero. So this is your maximum, this is your minimum, this is your lower limit and this is your higher limit. So this is less zero useful work and this is the maximum work useful. So if you differentiate with, and this is your maximum and this is your minimum, so maximum minus minimum is the actual. So in between there is the actual work, in between these two. So maximum work developed, S generation will lower, minimum work will develop, S generation is higher. So this is the reversible process and this is your highly irreversible process. To make this is a reversible, if this process is to make a reversible, you put a slice, very thin slice close to each other, and you remove one by one, you remove one by one. So the process will expand and it come again equilibrium, process will expand and come its equilibrium, process will come equilibrium, process will come equilibrium, process. So this is a very slow process, that means quasi equilibrium process, quasi equilibrium process. So it is a reversible, right? Okay, thank you very much. In the next video we will discuss about entropy transfer due to mass flow. Okay, thank you.